At 8:30 in the morning on August 13th, 2026, a short burst of movement traveled through the earth beneath the East Bay. It lasted only moments, yet it was enough to make people stop, look around, and wonder what had just happened. A magnitude 3.8 earthquake struck roughly 3 kilometers, or about 1.9 miles north of San Leandro, at a depth of approximately 5.6 kilometers, or 3.5 miles. The earthquake was close to the Hayward Fault, one of California's most notorious seismic structures. But why does a relatively modest earthquake command so much attention here? Is the Hayward Fault simply doing what active faults do? Or does this small tremor offer another reminder of a much larger force waiting somewhere beneath one of America's most densely populated regions? The earthquake was felt across portions of the East Bay and into the wider San Francisco Bay Area, according to reports, while the Bay Area rapid transit system temporarily reduced train speeds as crews checked infrastructure. The earthquake was initially reported at a higher magnitude before being revised to 3.8, and two smaller earthquakes, around magnitude 3.0 and 2.8, followed in the same general area. There were no immediate reports of major damage. The United States Geological Survey indicated that the earthquake's movement was consistent with the Hayward Fault, although scientists could not immediately establish whether the rupture occurred directly on the main fault or on a smaller associated structure. That distinction may sound minor, but it is crucial. The Hayward Fault is not a single perfectly straight crack slicing through the earth like a line drawn across a map. It is a complicated zone of fractures, bends, and smaller structures that collectively accommodate part of the enormous movement between two tectonic plates. An earthquake can occur close to the mapped fault without necessarily representing a major rupture of the principal fault itself. The August earthquake therefore should not be presented as a warning that a larger earthquake is imminent. At present, there is no scientific method capable of looking at a magnitude 3.8 event and determining that a magnitude 7 earthquake is about to follow. The significance lies elsewhere. The event occurred in a region where the Earth's crust is permanently under stress. To understand that stress, it helps to picture California not as a stationary piece of land, but as a landscape being slowly pulled and pushed in different directions by enormous tectonic forces. The Pacific Plate is moving northwestward relative to the North American Plate, and the boundary between them is spread across a network of faults, rather than concentrated along one perfectly defined fracture. The San Andreas Fault is the best-known expression of that boundary, but the Hayward Fault is another major player. It cuts through the East Bay, passing close to communities where millions of people live, commute, build businesses, and depend upon infrastructure that was never designed to remain perfectly still for centuries. The Hayward Fault is primarily a right lateral strike-slip fault. That description sounds technical, but the basic idea is straightforward. Imagine standing on one side of the fault and looking across it. During right lateral movement, the opposite side appears to move toward your right. The rocks on either side are essentially trying to slide past one another horizontally. They do not move smoothly everywhere, however. Friction can lock sections together while the tectonic plates continue pushing. Other portions can creep gradually. This mixture of locked and creeping behavior is one of the reasons the Hayward Fault is so fascinating and so difficult to predict. The movement itself is astonishingly slow when measured against a human lifetime. A few millimeters of motion may seem insignificant. A person would never stand beside the fault and watch California visibly slide northwestward. Yet over decades, centuries, and thousands of years, those tiny movements become enormous. The Earth's crust behaves like a material capable of storing deformation. When rocks are pushed, they can bend or strain. When the stress becomes greater than the friction holding a fault together, the fault can slip, releasing stored energy in the form of seismic waves. The earthquake is therefore not the beginning of the process. It is the abrupt release of a process that may have been unfolding for decades or centuries. That is where the August earthquake becomes part of a much older chapter. The Hayward Fault has been moving long before San Leandro existed as a modern city, long before railways crossed the East Bay, and long before the skyline of Oakland appeared across the bay. Its history is written not only in instruments and modern satellite measurements, but also in layers of soil, broken sediments, and displaced geological features. Scientists can excavate across the fault and examine those layers for evidence of prehistoric earthquakes. Those geological fingerprints allow researchers to reconstruct events that occurred centuries before anyone could record an earthquake with a seismometer. The geological record is especially valuable because written history captures only a tiny fraction of the Hayward Fault's life. Modern records begin after countless earthquakes had already come and gone. Researchers studying the southern Hayward Fault have found evidence for repeated strong earthquakes, with reconstructed intervals varying substantially rather than following a reliable timetable. One United States Geological Survey-supported study identified several prehistoric earthquakes and estimated a mean recurrence interval of roughly 130 years for part of the record, while emphasizing considerable uncertainty around individual intervals. Another United States Geological Survey timeline shows successive intervals ranging from about 95 to 183 years, with an average around 150 years. That variation destroys one of the most persistent misconceptions about earthquakes, that a fault becomes due in the same way that a train becomes late. Nature does not keep appointments. If a fault has ruptured at intervals averaging 150 years, that does not mean the next rupture must occur at exactly 150 years. An interval might be shorter. It might be considerably longer. The average is produced by looking backward across many events, not by looking forward to identify a specific date. The Hayward Fault has now gone more than 150 years since its major earthquake in 1868, which makes the long, quiet interval noteworthy, but it does not create a geological deadline. The earthquake that established the Hayward Fault in the public consciousness occurred on October 21, 1868. It was a major earthquake by any reasonable historical measure. Modern scientific estimates place its magnitude around 6.8, although historical estimates have varied. The rupture extended along a substantial portion of the southern Hayward Fault, and contemporary witnesses describe violent shaking, damaged buildings, ground deformation, and widespread disruption. Around 30 people were killed, a significant toll for the much smaller population of the time. In places, the surface was visibly displaced as the two sides of the fault shifted relative to one another. The world of 1868 was almost unrecognizable compared with the Bay Area of today. The population was dramatically smaller. There were fewer buildings, fewer bridges, fewer underground utilities, and far less dependence on complex transportation and communications networks. A major earthquake could devastate a community without threatening the enormous interconnected systems that now support modern metropolitan life. Today, the Hayward Fault runs through an urban environment containing homes, schools, hospitals, highways, railways, pipelines, power infrastructure, and commercial districts. The geological fault has not necessarily become more powerful. The human environment around it has become vastly more complicated. That difference is at the heart of modern earthquake concern. A major earthquake is not dangerous merely because the rocks move. It becomes dangerous because people and infrastructure occupy the landscape where the movement and shaking occur. Strong seismic waves can damage buildings, break water lines, disrupt electricity, derail transportation, and trigger landslides. In areas where loose or water-saturated sediments are present, the shaking can become more complicated because the ground itself can amplify certain motions or, in extreme cases, lose strength through liquefaction. The earthquake hazard, therefore, depends not simply on magnitude, but on where the rupture occurs, how it moves, and what lies above and around it. The Hayward Fault is especially significant because of its location. It is not hundreds of kilometers away from a major city. It passes through the urbanized East Bay. That means even an earthquake that is moderate by California standards can be felt sharply because the source is close to populated areas. The August event demonstrated that reality. A magnitude 3.8 earthquake is far too small to be compared directly with the great earthquakes that dominate California's seismic history, yet because it occurred only a few kilometers below the surface and close to San Leandro, people across the region noticed it. Bay Area rapid transit temporary speed reductions also showed how even modest seismic events can prompt precautionary responses in a highly connected metropolitan system. But there is a dramatic difference between the earthquake that happened and the earthquake scientists know the Hayward Fault can produce. The United States Geological Survey has created detailed shaking simulations for several possible future earthquakes, including magnitude 6.8 and magnitude 7.0 scenarios. The agency's scenario work indicates that the next large earthquake on the Hayward Fault will likely fall within the magnitude 6.8 to 7.0 range. These are not predictions of a specific future event. They are scientifically realistic examples designed to show how different rupture sizes could affect the Bay Area. The magnitude 6.8 scenario is especially important because it resembles the scale of the historic 1868 earthquake. In one United States Geological Survey simulation, rupture extends for roughly 54 kilometers or 33 miles along the Hayward Fault. Average slip is around 0.7 meters or roughly 2 feet. That means the earthquake would not be a single violent point beneath the city. A long section of the fault would rupture, releasing energy as the rupture traveled through the crust. The shaking would spread outward from that rupture, affecting communities across a broad section of the Bay Area. The difference between that event and the August magnitude 3.8 earthquake is therefore not simply a larger number. It is a radically different physical scale. The magnitude 7.0 scenario takes that scale further. United States Geological Survey simulations use longer rupture lengths and greater average slip than the magnitude 6.8 examples, producing stronger and more extensive shaking. A magnitude 7 earthquake is not twice as powerful as a magnitude 3.5 or 4 earthquake. Earthquake magnitude is logarithmic, meaning that every increase of one magnitude represents roughly 32 times more energy released. That makes the numerical gap between 3.8 and 7 extraordinarily important. The August earthquake released a tiny fraction of the energy associated with a major Hayward rupture. Treating the smaller event as a miniature version of the larger one would therefore give a misleading impression of what a future major earthquake could actually do. Then there is the magnitude 7.2 scenario, which pushes the possible consequences into an even larger category. The United States Geological Survey models this scenario as a simultaneous rupture involving both the Hayward and Rogers Creek faults. In the simulation, rupture begins beneath San Pablo Bay and proceeds in different directions along the two fault systems. Scientists emphasize that earthquakes involving multiple faults can happen, but they are considerably rarer than ruptures confined to a single fault. The magnitude 7.2 scenario is therefore best understood as a plausible but less likely extreme case, rather than the expected size of the next Hayward earthquake. The difference between those scenarios matters because it reveals something fundamental about earthquake forecasting. Scientists are not choosing a number and announcing that the next earthquake will have that magnitude. They are exploring a range of physically possible ruptures. A magnitude 6.8 earthquake could break a substantial portion of the fault. A magnitude 7.0 earthquake could involve a longer rupture and greater displacement. A magnitude 7.2 earthquake could involve two connected fault systems. Each scenario provides emergency planners, engineers, and communities with a different picture of what the future could look like. There is another layer to the problem that has nothing to do with the magnitude number itself. Earthquake shaking is strongly influenced by geology. The same earthquake can feel different in different places because seismic waves travel through different materials. Solid bedrock and soft sediment respond differently. Around San Francisco Bay, thick deposits of softer material occur in some locations, and these can influence the intensity and character of shaking. This is one reason a map showing only the distance from the fault cannot tell the whole story. The ground beneath a building is part of the earthquake hazard just as much as the fault several kilometers away. The Hayward Fault also has an unusual characteristic that can confuse the public. It creeps. In some sections, the two sides of the fault slowly move past each other without producing a large earthquake. Pavements, curbs, walls, and other structures built across the fault can gradually become offset as this motion continues. That visible movement is proof that the fault remains active, but it does not mean the entire fault is quietly releasing all its stored energy. United States Geological Survey research has long documented the coexistence of surface creep and the potential for large earthquakes. Historical and geological evidence shows that the fault has produced major earthquakes despite its ability to creep. This is one of the most important pieces of the Hayward puzzle. A fault can behave peacefully at the surface while remaining capable of producing violent earthquakes. Creep can release some deformation, but it does not necessarily prevent locked portions from accumulating strain. Imagine a long wooden beam under pressure with some sections slowly bending while another section remains rigid. Movement in one place does not automatically remove the stress from another. The actual physics of the Hayward Fault is far more complicated than that analogy, but the principle is useful. Seeing movement does not mean the entire system is safely unloading. The historical record becomes even more intriguing when scientists look beyond 1868. United States Geological Survey research indicates that another large earthquake occurred on the Hayward Fault around 1836. Although far less is known about that event than about the 1868 rupture. Geological evidence suggests that the fault has generated repeated major earthquakes over centuries. One United States Geological Survey study describes the Hayward Fault as having produced at least two large historical earthquakes, approximately magnitude 6.8 in 1836 and 1868. The earlier event remains poorly understood, but its existence reinforces the conclusion that the fault's history extends beyond the best documented earthquake of the 19th century. That long history is why scientists use the term seismic gap carefully. A seismic gap can describe a portion of a fault that has not experienced a major earthquake for a long period compared with its historical behavior. The Hayward Fault certainly attracts attention in this regard. More than 150 years have passed since 1868. While some reconstructed earthquake intervals have averaged around 140 to 150 years. United States Geological Survey materials have therefore described the fault as capable of producing another major earthquake at any time. But at any time does not mean tomorrow, and overdue does not mean predictable. The phrase expresses long-term hazard, not a countdown. The uncertainty is not a failure of science. It comes from the nature of the Earth's crust itself. Faults are irregular. Rocks vary in strength. Stress is unevenly distributed. Some parts of a fault are locked while others creep. Small fractures branch away from the main structure. Fluids may influence friction at depth. A rupture can encounter barriers or move through complicated zones. Scientists can measure many of these features, but they cannot observe every detail several kilometers below an urban landscape in real time. The Earth does not provide a simple pressure gauge that reaches 100% and rings an alarm before an earthquake. So is the Hayward Fault overdue? The most honest answer is that it has been quiet for a long time, and that long interval deserves attention, but the word overdue should never be mistaken for a prediction. The fault's past intervals were irregular. Some were shorter than the present interval, while others were longer. Earthquakes do not arrive because a calendar says the waiting period has expired. They arrive when the physical conditions for rupture are met. Those conditions cannot currently be observed with enough precision to provide a reliable date.